In this video, we are going to recover a private crypto key inside the Arduino just by observing its power consumption. We are going to perform a differential power analysis attack on an AES implementation. In the previous video, we have introduced what power analysis is and how you can prepare the Arduino board to do those measurements. And now we are going to actually solve the first side channel challenge of the RISC-your embedded hardware CTF. Piece of scake, SCA, side channel analysis, 100 points. So this is really a low amount of points, and I do have a lot of opinions about that. You will see. This is an easy SCA challenge using a cipher implementation without any SCA, so side channel analysis, countermeasures. Find the key used to encrypt and decrypt the messages. To encrypt a message, send the letter E followed by 16 bytes. To decrypt the message, send the letter D followed by 16 bytes. This sounds really easy. Should be a straightforward thing. Remember from last video how you can break a terrible RSA implementation by identifying the square and multiply operations in a power trace and simply read the bits of the private key? That's like the simple go-to example when introducing side channel analysis, because it's so simple. So from the beginning I set my mind to RSA. This is gonna be RSA. I just sent a decrypt command via serial to the board, trigger the oscilloscope at the right moment, basically trigger after I send the data to decrypt, and then the board will use the private key for decryption and I can just read the bits from the power trace. After the multiple days of fighting with the setup, soldering, knowing about ground loops and capacitors you should remove, and requiring all this fancy equipment, I was sure this is what I gotta do. I will be rewarded for learning all this with a simple challenge. It's the introductory side channel challenge anyway. Gosh, I was wrong. So I'm sitting there, staring at the oscilloscope, zooming around, trying different methods to acquire the data, like averaging traces or different resistors. I just didn't see what I would expect in an RSA power trace. This killed already multiple evenings for me, until I was more or less told this is not RSA. This is AES. Fuck my life. Also makes sense with the 16 bytes of data to encrypt or decrypt. That's the AES block size. A roller coaster of emotions, happiness of learning something new, followed by pure rage and frustration. This describes the whole challenge. So here's the thing. I knew the FAQ introduced differential power analysis DPA. I also learned about this in a hardware security class at university, so I knew that it's a thing, and I knew what kind of equipment I need to do this. But I did not expect this to be the case for the first 100-point challenge. In a few minutes you will see why they gave it 100 points. From a certain point of view it makes sense, but I completely disagree with it. So what is DPA? Differential power analysis is a more advanced form of power analysis which can allow an attacker to compute the intermediate values within crypto computations by statistically analyzing data collected from multiple crypto operations. These were introduced in the crypto community in 1998 by a company called Cryptography Research, and they are filthy rich now for discovering this and creating a consultancy research company around it. I mean, they deserve it, I guess. It's a pretty crazy attack. With simple power analysis, we assume that the implemented algorithm will perform different operations depending on the private key and thus show a different power footprint. But in case of the shitty RSA implementation, you could just multiply and square in every iteration and just keep the result of whatever the current bit was, thus no difference anymore. But there is a deeper layer than that. The power consumption directly comes from the single bits, the transistors. So even if the algorithm performs the same operations independent from the private key bits, those bits could still cause a very, very tiny different power consumption. This sounds even more crazy than the simple RSA example because these bits changes are so small. That's why you do a smart statistical analysis on a lot of collected traces. I actually don't want to explain this method in detail because it's fairly complicated and there's a good video by Colin O'Flynn doing exactly the AES example. But the gist is that you collect a lot of power traces from random input you encrypt. Then you make a guess on what the first byte of the private key could be, and then you perform part of the encryption algorithm as if it was the correct key. And given the random input value and that key guess, it would lead to different intermediate values. Then you take the traces where this intermediate value is the same for further analysis. If the key guess is correct, the power traces should all have correlation of power usage in that point in time. If the key guess was wrong, the traces you selected based on that would have completely different intermediate values, thus the random power consumption, and nothing would correlate. It would cancel out. So you do this for each possible key and for each possible byte, and in the end you should find the correct key. But how do you actually do this now? I knew I did not want to implement the math myself. Also, I would have to write my own tools to automatically collect these traces from my oscilloscope, and the USB and networking API seemed horrible. I wasted so much time and gave up on it. I knew what I needed. It was a ChipWhisperer. It's a piece of hardware that is specifically designed for doing this, and it comes with a software that has all these attacks already implemented. I thought about buying one initially, but I assumed an oscilloscope would be more flexible and I could learn more with it. I know some players spotted ChipWhisperer because it was recommended to use it for these hardware attacks, and it costs a bit of money. But I think without additional equipment like an extra oscilloscope, it's hard to debug issues. Anyway, I'm happy with my purchase choice. But I still wanted that ChipWhisperer for this challenge, and I knew where to get one from. Some of you know that I am still a student at the Technical University of Berlin. I'm still working on my master's degree, and we do have a small group at the university that does hardware security research. That's where most of my theoretical knowledge about these attacks comes from, and I have a fairly good relationship with them. And they obviously have a ChipWhisperer in their lab. So I wrote one of the PhD students and asked if I can come over and play with it. And that's the awesome thing about a university. You can get access to awesome equipment as well as help and advice. So I encourage every student to take advantage of these things. So when I used it the first time, I just followed the example, which is a DPA attack on the test board that comes with the ChipWhisperer. Everything is already set up for you. The test board has a connector for the probe. This is the measurement probe, and another broad connector which carries the power as well as RX and TX lines for serial communication. Then you use the example script, which implements a serial protocol to talk to the test board. Basically, it sends 16 bytes that should be encrypted, and with a click on start, it starts collecting power traces. The trigger for the power measurement and all the other parameters are already set to the correct values. Then you let the attack script run. It does the DPA, and after a few minutes or so, it finds the key where the power spikes correlated. And you can look at the fancy graphs and you can feel really cool that you just broke AES with DPA without knowing shit. And this is why this challenge only gives 100 points. Because in the end, it's just putting in the correct parameters and clicking go, and then the secret key falls out. Well, there's a bit more to that challenge, but essentially that's all it is. So I took the ChipWhisperer home and spent the next few days trying to do this on the CTF board. There were so many fails. I will tell them now in sequential order, but you have to imagine that they were all intertwined and only slowly I found all these mistakes. It was not a clear progression of find error, fix it, find next error, fix it. I tried a lot of things and spent hours over hours until I discovered these issues. So while I make it sound straightforward, it was absolutely not. It was hell. Okay, first of all, I had to learn how the ChipWhisperer framework works. I realized that the test board is just a little bit different from the CTF board. So I only have to change things like how to trigger encryption or decryption. But before the ChipWhisperer could communicate via serial with the board, I had to solve the issue of different voltage levels. The Arduino Nano board runs with 5 volt, while the ChipWhisperer uses 3 volt. So I had to build a unidirectional level converter to convert the 3 volt signal to 5 volt and the 5 volt signal to 3 volt. But that worked surprisingly quickly. So this is the setup. Serial connection via the level converter, and then using a Rigol probe to measure the voltage after the resistor. I was so happy and I felt really smart for using the Rigel probe because it fit onto the plug. Then I copied the code for the example script and spent some hours modifying that, and I was able to collect traces and ran analysis. I thought the difficult part was now to find the correct moment in time where the crypto is happening. At some point I realized that one of the LEDs flashes just before the crypto starts, so you could use that as a trigger for the ChipWhisperer. Again, don't forget the unidirectional level converter. But after a few days of not being able to find correlations in my captures, I was so frustrated and I finally decided to look into the serial communication. And I realized that I did not send the raw data I wanted to encrypt, but I sent it as a hex string. This was obviously completely fucking wrong. No wonder no analysis worked, because the data was just wrong. So at some point I had fixed that, but stuff was still not working, and it's really hard to figure out what's going on. The traces I took on the oscilloscope looked really good. I was able to easily see where the crypto is happening. AES has 10 rounds of crypto and you can clearly see them. They are right there. So my trigger was at the right moment. But when I took traces with the ChipWhisperer, I didn't see that. After many more hours and days, I realized the Rigel probe is the issue. You know, these probes are not just plain metal wires, they have some components in there. In fact, this probe is a 10-to-1 probe. So on the oscilloscope you actually have to set a 10 times multiplier for it. And the ChipWhisperer was not compatible with that. Once I realized that, I was about to jump off the next building. What the hell? Then I replaced the nice professional probes with a simple wire, and suddenly the measurements were great. Another challenge I had was to set the sampling rate high enough, because you want to sample a lot faster than the clock of the microcontroller. But setting that is super janky for the ChipWhisperer, and a lot of other small issues. The software constantly stopped working. I think it's a memory issue. I had to guess what certain parameters are for, and you can imagine with all the issues I just told you about and not really knowing what's causing it, it was overall a damn frustrating experience. Is it the capacitors? Is something broken? Is it interference? Is the script wrong? Are the parameters wrong? Am I collecting not enough traces? Am I at the wrong point in time? Is the trigger working? Is the data even random? I don't know. Oh, and I also lifted a second pin of the Atmega up because there are 2 VCC connections and I didn't know if that was maybe an issue. It was all hell. Anyway, once the whole setup was correct and working, and I clicked start to collect the traces, it started to look really good. Once you have a nice set of traces, you have to align them because the trigger is not perfect in time, but there are modules for that. And then you can run the analysis and the key magically pops out. There it is. I transcribed the key and hand it in. 100 points. 100 points for hundreds of euros I spent on equipment and days of work. 100 points. I am so depressed. I also have to give credits to Andres Moreno from Riscure, who despite my constant ranting and cursing still listened and helped me a lot. Thank you so much. Also, thanks to my friends at the TU Berlin and others from the Riscure IRC channel. I needed a lot of help for this challenge. But regardless of my hate for this challenge, I'm also really proud for having done it. It was so clearly above my skill level, and in the end I succeeded and I learned a lot.